Okay. Okay, folks, here we go. Welcome to the ASTTBC webinar, fourth in a series of 9 about SPM version 3. Topic is loading rates. A few webinar management details. Screen sharing is by GoTo. Once again, if that's working for you, you've got webinar management details on your screen. There's a chat window inside the GoTo set of tools, the screen that comes from GoTo. There's a chat box near the bottom with a plus, and if you click the plus, it expands the chat box, which is helpful. That way you can enter things and you can see what other people are entering. So the chat window. Audio is by traditional phone. Obviously, if you can hear me, that's working. Dial-in number and code was provided by email. And we choose that. The GoTo training has audio available within its own software, but voice over internet protocol is a bit twitchy. It is not very reliable, so we chose this as a rock solid option so everybody can hear the audio without delay. But the downside of it, of course, is that background noise. We've got maybe 20 phones open. So I guess I would ask you to mute your phone, and that's *6. So *6 on your phone, that is, to mute, and then *6 to unmute. We had, I think it was the first webinar, somebody had a jackhammer going in the background, it sounded like. So if everybody mutes their phone, that's very helpful. And that way I don't have to mute the entire group. So this may seem a bit childish to you, but I think it's necessary. If you don't mind, I need everybody to say something. So can everybody say mute? All together now. Mute. Okay, well at least one guy wasn't muted. So *6 to mute. And I guess I would suggest that you make a note, a sticky note or something. *6 to mute, and then *6 on your phone again to unmute if you want to ask a question or join a discussion. And on that regard, I'd encourage you to interject any time with questions or discussion and so on, especially if I misspeak, make an error, technical glitch. One of the webinars I said volume 2 when I meant volume 3, those kind of things. I'd encourage you to catch my error and interject immediately. That could be a technical glitch of other sort as well. So questions or discussion are welcome anytime. Or you can wait until the end of each module. Yep. Shut up, John. So you can wait every few slides, every 8 or 10 slides. I've got a slide will pop up saying questions, and that'll be a chance to ask questions about the slides we just looked at. The other option is to wait until after the presentation, and then we'll stay online as long as anybody else does for questions and discussion. And that's a good time to bring up questions unrelated to tonight's topic, for example, or enter into a dialogue about something or other. So *6 to mute, *6 to unmute. We are recording this webinar. The goal is to get it online. Right, to get it on our SPM Learning Resources page. But we're not recording you. We're not recording the phone conference. So your voice, your questions, and discussion are not recorded. In one thing, because that wouldn't seem very fair since we're posting it online. And for another thing, hopefully that encourages you to feel free to ask questions. There's no silly questions. Right? But if you then ask a question, in order to make the recording work for other people, I'll paraphrase the question. Right? So my voice will be the only audio being recorded. Just one more time. Everybody on the phone, mute your phone with *6 to avoid background noise. At least one person has still got the phone on. Nope. Nope. *6 on your phone, that sounds better. Thank you. And one person is still unmuted. Still. So *6 to mute, *6 to unmute. We'll see if that person realizes it. I hate to do this to you again, but can everybody say mute? 1, 2, 3, mute! Yeah, there's still somebody unmuted. We'll see how it goes. If he doesn't discover it soon, I'll have to mute everybody. So, a lot of people have already attended 3 of these things, so this gets a bit repetitive, so I'll try to keep this brief. My name is Jim Anderson. I'm the Compliance Officer, and I'll be facilitating the webinar series. My background briefly is as an excavating contractor. Septic systems have been a key part of that all my life. 55 years old, and about 12 years ago I transitioned into education. Teach heavy equipment operator trades programs, the ITA program, other trades related courses, do a lot of curriculum development. My educational background, I have a Diploma of Technology in Operations Management from BCIT, have my Provincial Instructor Diploma, and as a rope, I'm a planner, installer, maintenance provider, and inspector. Intended duration is an hour, followed by open discussion, questions, and so on. This is number 4 in a series. Pre-registration is required for each. I'll show you how in a second. Pre-registration, that means with the ASTTBC office through a link. The previous webinars are available on the SPM Learning Resources page, except for the last one, frankly. I'll try to get that up tomorrow. Let me actually go there. Here is my browser, so whether you're using Bing, Google, or whatever, you can find the webinar links and the learning resources this way. You can go through the front page, the ASTTBC page, but that's a bit of a convoluted path. So you can Google OWRP, On-Site Wastewater Registration Program, and that takes you to there, to there. Somebody's still unmuted. *6 to mute your phone. Whoever it is has another phone ringing in the background. Of course, if you hit *6 twice, then you're unmuted again, right? So that sounds better. Thank you. Okay, so we go to the practitioner side, and there's a link to the page we're looking for. This page is the launch page for OWRB, has a lot of helpful links, including documents, which gives you some planning examples. Somebody was asking about the SPM. There is a place where you can download a digital version of the SPM. Let's go back. We're trying to get to the Learning Resources page. There's the Learning Resources page, and it includes learning exercises that I did that'll be extremely helpful, especially if you need to write the exam. So these exercises have an accompanying answer sheet, and they'll help you self-assess your competency, help prepare you for the exam, or just help you improve your competency. We're talking about registration for the webinars, and if we click that link lower left, it takes us to an online registration page. There. So there's a list of still pending webinars, and if you click on the date, you then get to a page for online registration. Clear enough? Once again, a bit repetitive for those of you who have been here, so I'm trying to pick up the pace a bit, but these things are intended for several different types of folks. One is people who do not need to write an exam. They're just interested parties who want to review or improve their competency. Another group is the ropes who did not attend the workshops that Michael and I held across the province in October to January. Or you did attend, but you didn't successfully complete, which means that you either got 60% or less on the review exercises, or you didn't hand in your review exercise, or we couldn't read your name, or so on. The other group is ropes who are recent registrants since January. Those people have to write that same exam, so hopefully this helps them prepare for that. Another group is potential applicants who are just looking to find their way, to clarify expectations, and so on. Groups 2, 3, and 4 have to complete examinations by the end of the year. So somebody still has their phone unmuted. One more try. *6 to mute. And that might have worked. Okay. So again, groups 2, 3, 4 have to write an exam as a condition of ongoing registration, and this is intended to help you for that. I guess I'm going to have to mute the whole group of you. So now when I mute everybody, that means that if you want to ask a question, you don't have much choice but to enter it in the chat box. So I'm going to mute everybody here. Nope, sounds like whoever it was muted. Okay, you're still live. Let's move on. Introduction, a little more stuff. We hope that you use those learning resources. Need to point out that those resources and these webinars don't deliver the full range of required competency. Certainly not the competency you need to be registered, and neither the competencies you need to pass that exam if you're one of the people who have to write it. It's going to take a lot of additional work, self-directed study. The exam assumes that you've taken some training and that you have some experience and so on. CPD. If you're an ASTTBC member, you can claim CPD points for participation in the webinars. As you know, hopefully, if you've been reading ASTTBC emails, CPD is now a requirement. You have to do it, you have to record it, and you have to report it. CPD policy is available online. So from that policy, there's two categories for this within the description of acceptable CPD. One of them, self-directed study, indicates 1 point for every 8 hours. Another one that could apply lists 1 point for every 7 hours. So the registrar and I chatted about it, and we think it's reasonable to declare 2 hours for each webinar, even though it might be less than that. So that means 1 point for 4 webinars. Learning goals. Learning goals are good for you to focus on what it is you're trying to accomplish, and it helps me stay focused on what it is I'm trying to present. So we're trying to summarize key changes to loading rates, hydraulic and linear. HLR, hydraulic loading rates, LLR, linear loading rates. Key changes in version 3 of the SPM versus version 2. We need to learn to find the relevant standards and guidelines. For one thing, to do the work. For another thing, the exam, for those of you who write that, includes questions on what's the section identifier for this, that, or the other thing, or to I got distracted by a chat message, or to find a specific standard. So the chat message from John, did I hear you say that we have to register for each session, or are we credited for attending when we sign in? Arguably neither. There's nothing that says anybody has to take these webinars, and for CPD credits, it relies on your own ethics, really. So you report in your own CPD log what you've done, including this. So there's no automatic logging of this and so on. Thanks, John. The other goal then is to determine HLR and LLR for differing scenarios. In other words, make application as per the new ways, the new SPM. A little detail within these slides, within the presentation, direct quotes from the SPM are shown in italics. You might want to follow along in your own copy of the SPM, but if not, no worries. I will be displaying the SPM on screen. So let's get started. Hydraulic loading. So to set the stage, we want to define hydraulic loading, make sure we know what we're talking about. I came up with this definition, bit of a paraphrase of some others, and the quantity of effluent applied to the infiltrative surface, so that's the infiltrative surface of our soil dispersal systems, expressed as volume per area per unit time. So for example, liters per day per meter squared. So that's HLR, how much liquid we're applying per square meter to our drain field. Here's some out of the SPM. So that's SPM Volume 2, right? Standards, not guidelines. Section 5.5 says the HLR is a measure of the volume applied each day per unit area of infiltrative surface. Abbreviation we'll be using is AIS, area of infiltrative surface. And it describes the maximum allowable hydraulic loading rate, and it's based on maintaining the permeability of the infiltrative surface. In other words, loading it with a suitable volume of effluent that it will actually be permeable, that it will actually draw away the liquid without significant ponding. The other issue is to treat the effluent, soil-based treatment, within the unsaturated sand and soil. So if we made the system too small, then neither of those two things would happen. Hi Russ, star 6 to mute. So moving on, SPM Volume 3, a guideline then, says HLR includes consideration of the volume of effluent, so it goes back to that permeability issue, and mass loading. So mass loading of organic material is poo and food and so on, right? So mass loading is a measure of milligrams or some unit of mass per area. So HLR standards were established to make sure that we're not overloading the hydraulic receiving capacity of the soil, and also with regard to long-term clogging effects, in other words, mass loading, so that over time, 30 years, perhaps more, we've made the thing big enough to handle the anticipated quantity of organic material. So that's how they came up with this stuff. A little more definition. HLR is the volume of effluent applied to the infiltrative surface. So let's just look at what infiltrative surface means. A lot of you are very experienced, just bear with me. Some people attending are quite new. So AIS is the infiltrative surface area receiving effluent from the distribution system, or to put it differently, in drain fields, the drain rock original soil interface at the bottom of the trench or the bottom of the seepage bed or whatever, that's the infiltrative surface. Base of the trench, underside of the drain rock, or chambers. Right? So that's one version. The other version for mound systems is the gravel mound sand interface, in other words, top of mound sand, underside of pea gravel or chambers, and the sand original soil interfaces, and that is the basal loading rate, which is a different thing. So for sizing sand mounds, we use the mound sand HLR to determine the gravel mound sand interface, in other words, the area of the chambers or pea gravel, and the basal area interface underneath the sand mound, the native soil, basically, the scarified surface of the soil. So there's two HLR applications for sand mounds, and that's the definition of infiltrative surface. So at its very simplest, to beat the thing to death, simple trench system, it would be the bottom of the trench that we put drain rock on top of infiltrative surface. Minimum area of infiltrative surface, we work it out this way. AIS equals DDF, daily design flow, divided by the hydraulic loading rate. And that gives us the minimum, not maximum, minimum area of infiltrative surface. The cheapest way to extend the lifespan of a system or to assure better treatment is to make the thing bigger. Right? So it's minimum, not maximum. Let's move on. Linear loading rate. Linear loading rate is the volume of effluent applied per unit length of the overall system on the contour. So it's liters per meter, not liters per meter squared. And it's the overall system length on the contour, and a little more about that later, but that means that if linear loading says you need a system 100 feet long, you can't achieve that with 4 25-foot long trenches coming out of a D-box, right? It means that the system actually needs to be 100 feet long. You know, like 250-foot trenches with a center feet arrangement or something like that. More on that later. So system contour length. Select the minimum required system contour which is measured along the contour of the land. Right? So again, if the system needs to be 100 feet long, it needs to be 100 feet long from beginning to end along a level contour of the land. And there's how we work out minimum system contour length, DDF divided by the linear loading rate. So linear loading rate is a headache for most of us. Most of us run across a lot of parcels, a lot of lots that don't have adequate width to meet linear loading rate. I know I do a lot of work on lots that are only 40 or 60 feet wide, and then when you have a driveway running through one side of it, it's very difficult to put in a 100-foot long system on a 60-foot lot, right? So a lot of us have trouble with this. So the question I'm posing, I guess, is why? You know, why do we care? Why is linear loading rate an issue? And here's my attempt to answer that. The goal of making sure our systems are long enough is to maintain appropriate vertical separation, to maintain adequate depth of unsaturated permeable soil in operation. So the effluent dispersal to soil increases the degree of saturation within the VS column, obviously. Right? We're adding water, we're adding water with organics and so on in it, and that increases the wetness of the soil, the saturation within the VS column. So if we had 60 centimeters of unsaturated soil before we started, once we start adding effluent to it, we're going to have something less than 60 centimeters generally, and that's called a groundwater mounding effect. So it's increasing the elevation of saturation within the soil underneath our drain field, thereby, I guess, reducing the depth of unsaturated soil. So another quote out of the SPM, that mound, that groundwater mound or mounding effect continues to grow with time, and it can reduce VS to such an extent that VS no longer meets the standards. Right? So once again, if it was 60 centimeters, for example, that we needed, if we make the system short and boxy, we're going to end up with something substantially less than 60 centimeters in that example. And that means saturated flow, which means not an adequate retention time, not adequate treatment, and even potential breakout. Here's a quote from SPM Volume 3. In deep permeable soils, the water table rise will be very small. So deep permeable soils means, for example, something over a meter, maybe a couple of meters of sand, right? Permeable, highly permeable soils. In that case, LLR is not very relevant, or the system length issue is not difficult, because we're not going to have much mounding effect. But in clay soils or finer soils, it needs more head to drive the water through the soil, right? And so the higher the groundwater mounding effect will become. A little typo there, I see. So in finer soils, we need to make the system longer, basically. Slope comes into play. On a sloping site, the mounding effect will be smaller as the slope gets steeper. So, bear with me here a minute. I had a note to show you 3 5.6. So once again, in the digital version, we have the table of contents overall. Volume 3 has guidelines. Section 5.6 is minimum contour length. And I guess my goal is to access these sketches. Bear with us, those who are experts at all this stuff. So first sketch, we've got not much mounting effect, maybe deep permeable soils. Second sketch, we've got a restrictive layer, so the water leaving the infiltrative surface is going to go sideways down at that restrictive or semi-restrictive layer. Next sketch, over time, especially in finer textured soils, the level of saturation starts to mound, starts to rise. If we have a longer system, that effect will be less pronounced. If we have a short boxy system, it'll be more pronounced. So it's reducing the amount of vertical separation, like so, right? Next diagram. Higher mound for same flow to lower permeability soil. Mounded water table. Slope reduces the effect, similar to pouring maple syrup on a plate. If it's a level plate, the mound of maple syrup will be higher than if it's a slope plate. Right? It's probably intuitive. Yeah, should I keep going with that? Let me think about this now. Sure. So on a sloping site, then it tends to work its way down into the receiving soil. So the receiving soil, the downslope area, is important to consider for the LLR as well. This diagram is meant to illustrate the point that if we need a 100-foot long system, we need to arrange it this way. Now we might break it up. We might break it up with 3 different entry points, whether they be D boxes or manifolds. But that system is 30 meters on the contour. This system up in here is not. This system is 10 meters long. So it doesn't meet a minimum system length of 30 meters. That system is only 10 meters. So most of you get that, but those of you that don't have missed something fairly important. And I think I'll leave it at that for now. We'll go back to that later. Any questions or discussion on that portion of it? So *6 to unmute. Or did I mute everybody? Oh, it sounds like I didn't unmute you. So 2 guys on, yeah, go ahead. Yeah. Correct. Yeah, correct. And we'll look at that option towards the end of it, but exactly right. There are a couple of things we can do, including, as you described, separate them. We're supposed to have an interceptor ditch between them and so on, but you're quite right. Very good, yeah. Did someone else had a question? You bet, yeah. And feel free. Any other questions? Okay. So one of the goals, learning goals, was to locate these things, to be able to identify or at least find your way. So again, it's a bit repetitive. Standards are in volume 2. So if you're looking for loading rate standard, it's in volume 2. And those are musts, right? Ropes have to comply with standards, have to comply with volume 2. Actually, all authorized persons have to follow the standards once the SPM is declared as the source of standard practice on the health form, including professionals. They're linked standards, so you can't cherry pick them. Even if you're a professional, once you are using the SPM, you actually have to follow volume 2. For ropes, departures that ropes may consider, say to linear loading, have to be supported by a professional in writing. That does not mean you have to give up the entire job. You just need a professional to establish what you're going to do about the system being shorter than it otherwise should have been. So we all need a relationship with a professional for this and other reasons. So the topic is how to locate things. So if we're looking for standard, it's in volume 2. Guidelines, on the other hand, are in volume 3, and those are shoulds. So ropes can depart from guidelines only if supported by written rationale. But in this case, that's written rationale by the rope, right? Not a professional. And that written rationale has to say why you couldn't follow linear loading, for example, what the mitigating strategies are, and some assurance of equal to or better performance than by following the guideline. I'm going to move on because we've done that in all the other 3 webinars, but that's the brief version. So the topic is how to find these things. It's in section 5 in both volume 2 and volume 3. Right, it's a core planning standard, which is in section 5. Section 6 has construction specifications. Section 7 has maintenance stuff. So the section number is 5. Volume 2 includes the HLR standards in section 5.5. Volume 3, same section number, right? Corresponding sections, includes HLR guidelines, explanatory material, and quite a few examples of how to work this stuff out. The actual tables are in volume 2, section 5.5, 21 to 25, and in my paper version I've got a sticky note there protruding from the manual, which is labeled HLR, if you know what I mean. You may want to do that as well. And we'll be looking at those tables several times tonight. LLR, linear loading rate, it's still in section 5 because it's a core planning standard. It's now section 5.6 instead of 5.5 was HLR, so 5.6 includes the standards. Volume 3, same section, includes the LLR guidelines, explanatory materials, and so on. And the actual tables in volume 2 are 26 to 28. So in my paper version, I have another sticky note there that's labeled LLR. Any questions or discussion on that bit? Probably not. That was fairly simple. All right. Just to keep you interested, let's try an example. Basically with the goal of making sure we know how to locate things. So the question is, what's the maximum HLR for a specific set of characteristics? Let's see what I can do here. So table of contents in a digital version is very helpful. We know it's in volume 2, section 5, and the question was hydraulic loading rate, so we're going to go to section 2, 5.5. Make this a little bigger for you. And the maximum allowable loading rate, it'll be one of those tables I mentioned. Am I there? Sure. So sandy loam shows up there, right? Sandy loam, and the question tells us that it's got a favorable soil structure and consistence category. Structure and consistence category, sandy loam, favorable. It was type 1, so the answer to the question is 27 liters per square meter. Next question. Different soil, same question, hydraulic loading rate. So clay with very poor soil structure and consistence category. Let's have a look. Clay shows up there. Very poor is there, and the answer is not allowed. So it's another example of sort of a site capability standard. Not allowed means that we can't disperse to it. So if it is those things, if it's clay with very poor soil structure and consistence category, then we can't disperse to it. It becomes a limiting condition. So that means that we would have to maintain VS above that clay layer, 60 centimeters for example. So we can't disperse to it if it is clay, period. Well, that's not quite true. We could if it had favorable soil and structure consistence category, but since it doesn't, it's just not allowed, period. Another example, now we're into linear loading rates. So slightly different information because we need the soil texture, sandy loam. We need the structure and consistence category, which the question tells us is favorable, and we need slope and soil depth. So LLR was section 5.6. There we go. And the table that we're looking for, at least to get us started, is this one. And the information in the question, it was sandy loam favorable. So sandy loam favorable, so we're somewhere in there. And the information in the question, 5% slope, and I hope we understand that's perpendicular to the longitudinal axis of the dispersal system. Right? It's perpendicular to the length of the thing. It's the slope at right angles to our system. And 50 centimeters soil depth, and that's soil depth below the infiltrative surface. It was 5%, so it does not belong over there. That's less than 5%. It's in here somewhere. The soil depth below the infiltrative surface, that's natural native soil, unsaturated and permeable, was 50 cents. So that puts us in there. And if I remember right, it was sandy loam favorable. So I am seeing 60. I think that's our answer. 60 liters per meter. Hey Rick, star 6. So it's 60 liters per meter, not meter squared, and so on. So our answer was 60. Next question. You're probably on to me. Clay, poor soil. You already know the answer. Not allowed. Right? So clay, poor, very poor, not allowed across the board. So it's a limiting condition. And we would have to maintain VS above that. Okay. Any questions or discussion on that? Excellent. So let's look at some key changes in version 3 of the SPM as compared to volume 2, and they're pretty significant. In volume 2, 5.5, it hinges on new soil structure and consistence categories, table 221, and that's that favorable, poor, very poor, or not allowed. So let's have a quick look. Table 221. Table 221 gives us this soil structure. Soil structure and consistence categories. What do we want to say about it? Well, it doesn't list texture, interestingly enough, except for a mention or two like there. It's based on the structure. And consistence up in here. So between the two, perhaps it's self-explanatory, we use this table as a first step in determining our loading rates to determine whether it's FP or very P, favorable, poor, or very poor. Favorable, poor, and very poor soil structure and consistence categories have nothing to do with the USDA soil standards or Kansas or anything like that. It's a SPM strategy to simplify things. There you go. So moving on, it hinges on new soil structure and consistence categories, and then the next thing is not really new. It actually always was this. You select hydraulic loading rate based on either texture and consistence category or permeability or perk rate. Permeability being field saturated conductivity from permeameters, and perk rates as a hole in the ground we fill up with water. It was always that way. In the old SPMs, we had two columns, one for soil texture and consistency, another for permeability, and we were supposed to choose the most conservative outcome of the two. But now, to make that crystal clear, they put that in two distinct tables. So there's the one for based on soil type, and once we determine our hydraulic loading rate or linear loading rate in the other table based on texture and our structure and consistence, then we check it, if you like, against another table based on permeability or perk rate. So there's our permeability, there's our perk rate, and there's the corresponding loading rate. And if those two are the same, that's easy. If they're not the same, then we have to choose the most conservative of the two, just like we always did, frankly. And what's the most conservative? If the loading rate was, say, 27 here, and then down here it was, say, 30, which one do we choose, 30 or 27? Well, we choose the one that creates the bigger drain field, which would be a smaller hydraulic loading rate. So in that example, we would have chosen 27, if I didn't mix up my analogies here. So that's a pretty significant change. Certainly that soil structure and consistence category, favorable, poor, and very poor, is brand new, and the presentation is completely different. So since we now have to use that two-pronged approach, we better make sure we understand soil structure. And so as briefly as possible, I don't intend to teach a soils course tonight, but a helpful reminder for experienced folks and critical knowledge for new folks. Here's the glossary definition of soil structure. So it says the arrangement of soil particles into definable aggregates. So that means that individual soil particles have glommed together, to use an unscientific term. They have formed PEDs. They're kind of stuck together into PEDs. Now those PEDs are characterized and classified on the basis of size, shape, and degree of grade or distinctness. Let's define PED. PED is a single unit of soil structure. In other words, a bunch of individual particles came together into a chunk. And that PED can appear as a block, a plate, a column, or some other things. So that's a PED. The shape of the PED then refers to the type of PED, and those terms are used interchangeably, shape and type. And those are either granular, blocky, platey, columnar, prismatic, and so on. So a block of soil is a PED, and if it has a PED, then it has soil structure. Now grade. So, structure is classified based on shape. So far so good. So that could be block, plate, or so on. And grade is either weak, moderate, or strong. Let's look at grade. Here is the glossary definition. Degree of distinctness, or the degree of aggregation, how well the structure is expressed in place. In other words, how visible it is. And I left this in because this is an important point I need to remember to make, is refer to U.S. Department of Agriculture Soils book, or the Kansas Canadian System, what is it now? Canadian System Soils Information System. So we need a copy of at least this one, and that's available for free online from the USDA. USDA, what is it, Field Book for Characterizing Soils or something like that. So we need that as one of our reference books. You can even get the paper version for free. At any rate, back to grade. So grade, in my sort of truck driver terms, it describes how visible the individual PEDs are in situ. In other words, in the test pit face. So how easily you can see them. If the grade is weak, then, for example, blocky PEDs would be barely visible. You might not even be able to really discern them until you start poking into the face of the test pit with a small shovel or something. If it has strong grade, you can clearly see the blocks in the face of the test pit. So that was structure type, structure grade. Let's move on to consistence. So consistence, the glossary says, degree of cohesion and adhesion. In other words, how firmly the individual soil particles hang together in a block or plate or prism or whatever. Or resistance to deformation or rupture. In other words, the rupture resistance of a PED. So consistence includes the resistance of the soil to rupture, the rupture resistance, or the resistance to penetration. In other words, how difficult is it to put a shovel into it, for example, and the manner in which the soil behaves when subjected to compression. So in other words, it's how hard the things are. Right? If it's a block or a prism, consistence refers to how much force it takes to break it. But then, just to confuse us, the other consistence categories are for structureless soils, including loose. So loose is a consistence, which means that it's not aggregated, it's not in PEDs, it's a handful of sand, right? Individual particles, no blocks, no plates, no prisms, or cemented. The other type of structureless soil is massive. So think hardpan. You know, clay hardpan has some degree of cementation, and in that case, it doesn't have PEDs, and it's not loose. So then the consistence becomes some degree of cementation. A photo, hopefully, to illustrate the point. So this is a blocky PED at my fingertips. The structure type or shape then is blocky, probably subangular blocky. The grade, I would suggest at least, is strong. You know, in the test pit you can see these things super clearly. And so the grade is strong. The consistence, the rupture resistance of the pit, of course we can't really tell from a photo, but you can kind of get an intuitive sense that it's fairly hard. I think it was hard in this case. And again, back to the USDA manual to really figure out how to determine that, but it's a measure of how much pressure it takes to burst the thing, right? Next picture. Again, it's the same site, by the way, maybe a different test pit. So the type or shape is blocky, subangular blocky. The grade is strong, very strong in fact. I mean, they come right out in my hand, you can see them clearly. You can see these things in situ in the test pit phase, so that's strong grade. Consistence, we're guessing at because it's a picture, but you'd be right if you guessed hard or stronger, right? It takes quite a bit of pressure to burst these things. So just let me go back to table 221 just to be clear. You know, these PEDs, they are blocky for sure. Right? It's not a sandy loam, that's for sure. So our category is going to be in here somewhere. Consistence, it's dry consistence, right? The soil in the test pit is not wet, it's dry. And so it's going to be over here, hard or stronger rupture resistance. So blocky, that means that the soil structure and consistence category is not allowed. Right? So to be clear, this photograph, I selected it not because it's good soil for dispersal, it's in fact very bad soil. The reason is that pictures of strong grade and hard consistence make the point very clearly on what those distinctions are. On that topic, why is this unsuitable? For one reason, because it's hard consistence, right, at the right hand column of that table. The other reason is seasonal high water table. Right? This soil is seasonally wet, and that's why we get mottles. This is actually a very good picture of mottling. Those are all redoxomorphic features, in other words, rust. So part of the year this soil is wet, part of it is dry, hence we get rust. Arguably even this white stuff is a type of redoxomorphic feature, but more to the point, you get that rust stain. So this is unsuitable soil. The other indicator is root growth limits. The top of the picture is cut off, but the very surface layer had lots of roots, healthy looking roots. These sickly little things indicate that it's a limiting condition, right? Seasonal high water table. It's not a complete absence of roots. Often it's just a transition from abundant root growth to sickly little things like this. So this is very poor soil. It's a limiting condition. We would have to build a system at least 60 centimeters above any of this stuff. So moving on, I guess. This is granular structure type. A lot of people confuse granular structure type with single grain loose. Single grain loose is exactly what it implies. It's a handful of individual soil particles that do not aggregate together into PEDs. So sand is loose. This is not that. Right? This is granular. Sand can have loose consistence, but highly unlikely it has granular consistence because it doesn't have any PEDs. So granular kind of sounds like it would be sand, but it's not. That goes horribly wrong. It's one of the most common things that our folks at ASTT identify immediately as a significant error in soils reporting. Granular structure type implies that it has pea-sized PEDs. First of all, that it has PEDs at all. Secondly, that they're pea-sized. We don't mean it precisely. You know, it could be smaller, it could be bigger than a pea, but it's meant to describe an actual PED. So that's granular structure type. Sand is loose. One more picture of granular. Not that helpful because it's got no scale attached, but that's granular soil, often found in surface horizons of sandy loam and so on. So that's our little review on soil stuff. Maybe I should ask, I don't have the screen up. Anybody got questions about that? Okay. So some more key changes. Continuing, if you like, the topic of changes to hydraulic loading rates. It uses new soil texture groups. Table 3.1. Bear with me. It's volume 3. Table 3.1 is in here somewhere. 3.4. I did prepare, honest, I did. Where the heck? Oh, I'm sorry. Table 3.1, that would be my error. It's in 2, so 2:24. That didn't work. I'm way out to lunch here. Let's try it this way. Table 2:24 is there. Still wrong. Hard to tell, but I actually did prepare. I'm just trying to talk and think at the same time here. Bear with me. So it's page 3:12. Let's try that. 3:12. There we go. Sorry about that. So the point I was trying to make was that the HLR tables and the linear loading rate tables, they group the old soil textures into common groups, if you like. Table 2, there we go. So on the right is the old USDA texture classifications, all of them. And if you remember, the old loading rate tables had over 100 little boxes on it. It was fairly difficult to use. So in an effort to simplify things, they grouped these USDA texture classes into simplified groups. Right? So this is an effort by the SPM authors to simplify things. So that's a change, perhaps a significant one. Another change is new clarity regarding sand media loading, table 224. Let's see if I have any more luck at all with that. Table 224, sand loading. It'll be in here. Volume 2, section 5. Sand loading is there. Table 224. What do I want to say about it? As you know, probably, the old SPM essentially said we can't use just good old C33, we had to use mound sand, and then there's the loading rates, which have been rounded a little bit but are relatively the same. The problem with it is that in lots of areas of the province, we can get concrete sand, we can get C33. Mound sand is C33, but C33 is not mound sand necessarily, because C33 can have up to just less than 10% fines, whereas mound sand has a more stringent restriction on fines, and if you can't find that, then you're breaking the rules essentially. So the new SPM has made it crystal clear that you can use alternate types of sand. You just need to make the system smaller in this case. So if you had clean coarse sand with more, fairly significant fines in it, you can still use it. You just have to use a lower loading rate, therefore a bigger sand mound. So that was a welcome change. Some new how-to stuff. So 3 steps leading us to the answers. It's sort of a 4-step process. The first step is select the soil structure and consistence category based on the soil evaluation. So during the soil evaluation, we determine the type and the shape, single grain, massive, or blocky, platy, prismatic, and so on. Consistence then is the rupture resistance of the PEDs, if there are any, and if there's no PEDs, it's either cementation or it's loose if it's sand. So just to be crystal clear, it's this, right? Soil structure and consistence categories based on structure and consistence. The next step then is that we select an HLR based on the soil texture and the consistence category. So we've determined whether it's F or P. Then we go to the table 222 and choose or select the hydraulic loading rate based on soil texture, structure, and consistence category. The next step is to use the next table to do that 2-pronged approach to check it against the next table based on perk rates or permeameter results. We'll do some more examples of that, but I think you're getting the gist. And then we use the lower of the 2 HLR values as the maximum allowable soil HLR, so the most conservative. Let's do an example. So there's the data. So you remember the first step then is to determine the structure and consistence category. Next step then is to determine an HLR based on that. The third step is HLR based on permeability. Let's try to start with, so I put that down there, structure and consistence category. So there's our categories, and it tells us that it's sandy, loam, blocky. Well, this table doesn't list all the textures, but it does mention sandy loam or loam. So this has caused some confusion. This doesn't mean that all sandy loams fall in here. It means those sandy loams that have weak grade platy structure falls in here, just to be clear. So that's not us. That doesn't relate to this question because it says it's blocky structure, not platy. So for that reason, the relevant column, what does it say? Weak? It means that there's our relevant row, I should have said. Okay, what else have we got? It says it's weak grade and slightly hard consistence, which puts us there. So the answer is P, poor. Everybody happy? So the next question then gives us the 2-pronged approach, right? The rest of the data we need is permeability or perk rate. So we can take that poor, we can go to the first step. Perhaps I should have done that first. What was it? It was sandy loam, it was poor, so the answer was 23. The second step based on our perk rate then is, next table, perk rate is 20 minutes per inch, which falls in here, and the answer is 23. So there was no contradiction between the two approaches. So the answer is 23 liters per square meter. The next part of the question then is, what's the required AIS for a DDF of 1500? So we take 1500 DDF divided by the hydraulic loading rate of 23 equals 65 square meters of infiltrative surface. So either our bed needs to meet that, or our point of application for CTDS, or the sum of the trench bottoms, and so on. So there is one quick example. Let's look at system contour length. Just a reminder, please place your systems along the contour. We have a lot of people, or a lot of failures, where people are putting their system down the slope, which is just bizarre to me. If you had a minor slope and you had let's say a 50-foot long bed, and if the slope was minor enough that you could still have the right cover soil depth with a level infiltrative surface, you've got half of it, right? You've got a level infiltrative surface, but the mounding effect at the downslope end is going to be significant. They have to go along the contour on a level line across the land. The other thing we need to make sure we get is that system length is the length on the contour, not the sum of trench lengths. Right? So 3 50-foot trenches from a D-box is a 50-foot long system, not a 150-foot long system in terms of linear loading and minimum contour length. So some of the changes. New linear loading rate, it generally allows much shorter systems. Me and a lot of other people complained quite strongly that linear loading was killing the industry. All these numbers up in here are way bigger than they were before, which allows us to have shorter systems. Michael just did the math, and he's got a lot of experience doing in-situ groundwater mounting studies and so on. So they justified this by good old BC knowledge and engineering calculations. So this was a very welcome change. It makes a huge difference in a lot of cases because these numbers are so much larger. Very welcome change. Frankly, the numbers, once you get down in here, are the same. They've just been rounded. So we didn't get much help for the finer textured soils. Let's move on. The other changes are similar to HLR. They're linked to those new texture groups, right, where they lumped different textures together, and structure and consistence categories, fair, poor, very poor, and so on. We select LLR using either texture consistence or permeability perk rate, right? And we choose the most conservative of the two. Applicability. Again, two-pronged approach. First, you determine structure and consistence category. Poor, favorable, very poor. This is slightly different from the HLR. We select the linear loading rate based on the soil horizons in which water will flow from the dispersal area, not necessarily the horizon at the infiltrative surface. More on that later. Again, similar to HLR, we first selected based on soil texture and consistence, and then we check it against soil permeability or perk rate. So we use this one as the second approach, right? We base it on soil type, and then we check it against the next table, which has field saturated conductivity and perk rates, and then we choose the lower of the two. What else have we got? Here we go. I said we would get back to this. For assessing LLR, the soil layer of interest is the soil layer at and just above the depth of seasonal high water table. For hydraulic loading rates, it's the opposite. For hydraulic loading rates, we're assessing the soil, or we're basing it on the soil characteristics 30 centimeters below the infiltrative surface, from the infiltrative surface to 30 centimeters below. So if the soil changed at 35 centimeters, we're still basing hydraulic loading on the upper 30 centimeters, but for linear loading it's the opposite, because we're worried about the mounding effect down at the seasonal high water table or restrictive layer. So we're basing it on the soil types and consistence there. Now that might be the same, but it might not, right? There could be a horizon change within the vertical separation column. And then if there's no seasonal high water table, then we're interested in the flow restrictive horizon, or the soil characteristics there. A few examples. We'll look at the tables. Linear loading is the topic, and here's the data. So let's look at 227. We have to start with the structure and consistence category. For both hydraulic loading and linear loading, we have to go back to this table. And the question says sandy loam texture. So sandy loam does show up there, but only if it's platy structure. And in our case, it's not platy, it's blocky. It's blocky weak, so we're up in here. We're in there. Hard dry consistence. Hard dry consistence puts us over there. Can I screw that up? Let me think about this now. That wasn't what I intended. Oh, I'm sorry. It says weak grade, slightly hard consistence. Well, that makes me feel better. So weak grade, slightly hard consistence, it's poor. So our category is poor structure and consistence. So now we can go to table 227 and 228. Table 227. And we have sandy loam. We had poor, so we're in here somewhere. And then the question gave us slope and depth. 8% slope, so that would be in that column. 50 centimeters VS falls in that column. And it was sandy loam poor, so it looks to me like it's 50. 50 liters per meter is the answer so far. But we have to check the next table. Permeability. And the question said 20 minutes per inch. Oop, screwed that up. That's not supposed to say any of that. My mistake. But 20 minutes per inch, let's go there. So 20 minutes per inch is in here. Our soil depth was there. So it is still 50. Still 50 liters per meter. There was no contradiction. So the answer is 50 liters per meter linear loading rate. So in that case, what's the minimum system length for 1500 liters? And it is 1500 liters DDF divided by 50 liters per meter LLR equals a system length of 30 meters, 100 feet roughly. For sandy loam. It's a long system. Any questions or discussion? Anybody? Sounds good. All right. We're getting kind of close to the end. There's some more examples. There's the data. HLR question, not LLR, HLR. So we have to start with structure and consistence category. It's single grain loose. Single grain loose, as you might expect, is favorable. But let's just have a look. Single grain means it's sand, maybe loamy sand. And single grain is a good thing. And our texture group there, single grain, loose, favorable. So it's a favorable soil category. Then we go to the reason the question says extending to at least 30 centimeters below the infiltrative surface is that's the relevant soil for HLR selection. We talked about that. If it was LLR, it would be the soil down by the limiting condition. So single grain structure, loose consistence, permeability. Now we have our two-pronged approach, if you like, our two different tables. First one is here. What did the question say? The question said fine sand texture. So fine sand, note that there's different columns, right? There's sand, there's gravelly sand, coarse sand, fine sand is a different row, I should have said. It's favorable structure type because it was loose. So it's type 1. So the answer so far is 27. Did I screw that up? 27. Fine sand texture. Favorable. Sure. Okay. 27. So now our next check, if you like, against permeability, and the question said 2200 millimeters per day field saturated conductivity from permeameter testing. So 2200 falls in here, and it's still type 1, and now our hydraulic loading rate is 35. We had 27 from this table, and we have 35 from this table. So now we need to select the most conservative of the two. So the answer is, it is going to be 27, right? 27 liters per square meter, because that gives us a bigger system than 35. And to wrap up that question, how big does this thing have to be for a 1300 liter DDF? So it's 1300 divided by 27, not 35, gives us 48 meters squared, or square meters of AIS, trench bottom or bed bottom. Linear loading. There's the data. Linear loading, just like hydraulic loading, we have to go back to the soil structure and consistence categories. And the question said fine sand, single grain structure, loose. I guess I didn't have to go back there. It's favorable still. Right? Now it's asking for linear loading. So the linear loading rate table is a little bit further on, section 5.6. So here we go, linear loading. And now we need the slope, 2%, depth 65. Fine sand is there. Slope was 2%, depth 65, so that puts us in there. So if I did this right, thinking and talking at the same time, the answer is 70 liters per meter. We then have to check the next table for permeability, and it was 4 minutes per inch. I chose 4 because it seems odd to me, maybe it's arguably an error, that 4 shows up there and there. You know, arguably this should have been, you know, less than 4. But there you go. It is what it is. We could always choose the most conservative of the two, although in this case it makes no difference. For either, it would have been 70. So the answer is 70 liters per meter from both this table and that table. They were both 70. So we're good to go. And then to wrap up that question, what is the minimum system length for a system? Sorry, for a system with 1300 liters DDF. 1300 divided by 70 means that system needs to be 18.6 meters long. 18.6 meters on a level contour. What for a sand mound system? Length for a sand mound. There's the data. So, once again, we need to start with structure and consistence category. We're getting good at this now, right? Let's hope. Structure and consistence category. And the question told us that it was silt loam, weak, blocky, slightly hard. So weak, blocky, slightly hard looks to me like it's poor. I think I got that right. So it's poor structure and consistence category. Now we go to what that happened. Now we go to Linear loading rate tables. And it was silt loam, so we're there. Excuse me, I apologize for all this coughing, it must be very annoying. It was a poor category, silt loam. The slope was 6%, which puts us over here. 30 centimeters of native soil VS puts us there. Silt loam. So if I'm reading that right, the answer is 45. No, I think I screwed that up. Silt loam. It was P. It was poor. My mistake. So the answer is 35 liters per meter. Check it against the permeability table, and the permeability was 28 minutes per inch. 28 minutes per inch falls in there, and the slope was 6%, so it was over here. The depth was 30 centimeters. So if I got that right, we're looking at 45 liters per meter, which contradicts the 35 that we got up here. So we choose the most conservative of the two, which is the smaller loading rate, resulting in a bigger system. So the answer then is 35, the smaller loading rate, bigger system. To wrap up that question, base it on DDF, what's the length? So the length is 1500 liters DDF divided by 35, the most conservative of the two loading rates, means this system needs to be 43 meters long. 43 meters. A lot of parcels don't have room for that. So what do we do if we can't meet LLR to wrap up the night? Another few slides. SPM Volume 3, the guidelines, has a section titled Sites Where System Length is Constrained. In other words, when we have the challenge meeting linear loading rates, it has that subsection that deals with a sand mantle sand mound. So in that section, it starts with a little flip. It wants us to go back to this section, and we'll do that. That is section 3, volume 3, 6.15.2. There's a regular sand mound. Okay. And there is a sand mantle. So this is new. Sand mantle, sand mound is just an extension of the downslope toe, and I hope that makes intuitive sense. That would what would we say? It would allow us to have a higher degree of mounding effect in the soil and still not break out. So it allows that mounding effect to stretch out down the slope, and we still have a decent volume of unsaturated permeable soil to make all that happen. And in that case, we can use a linear loading rate of 50, which back in our example was a lot better than 35 or whatever it was. So a sand mantle, sand mound allows us to use a linear loading rate of 50 if the underlying soil had a less favorable loading rate, like 35 or 40 or something like that. So that's a fairly helpful change. Just to illustrate the point, this is a sand mound, Dawson Creek. You can see the slope. There's no significant constraints downslope. That slope is a good thing, right? It allows us to make a shorter system, especially with an extended toe. And so I guess the reason I put this picture up was to illustrate the point. This is where we're going to extend the toe, right? So we're going to scarify it a little further. Eventually I think we're extending it down to here, but for now we're still running the hoe up and down on the grass. So we scarify the receiving soil. While we're here, we need to have mound sand or clean coarse sand underneath this thing. New SPM allows us to have other types of soil. In other words, I do not need to put C33 down here, which is a good thing in this case, because the mound sand was coming from Fort St. John. It was about a 5-hour round trip, extremely expensive. We can use soil with decent permeability for cover soil and for toes. And the pit run came from up the street. It was about a 20-minute turnaround, remarkably cheaper. So that was a sort of a sidebar issue. But now we're going to look at the next picture from the other end of the mound in a finished condition. Well, not quite finished. It's not raked off yet. I just smeared it off with the hoe. But you get the idea that we had some pit run in here, and we had a lot of pit run in there, and then we covered it all up with some native topsoil. So that's sand mantle, sound mound, extended toes, allowing a shorter system, linear loading rate of 50 instead of this soil would have been really poor. It would have been something like 25 or something like that. As it was, I think the system was over 30 meters long, and the house wasn't all that big. Some more stuff. If we can't meet LLR, what else can we do? I forget who it was brought up this point much earlier. We can have relief drainage. So we can install the thing in a series of stacked cells on the slope with interception drains. And the interception drains is required in order to meet SPM. Seems like a good idea. And probably the best thing we can do is look at the diagram, but we do need to maintain horizontal separation from the dispersal systems to the interception drains. And let's have a look at figure 3.6 to illustrate that point. 3.6. Table 3.6, come on. Oh my goodness. I guess I'll do it another way. 3.6 into 3.6 system length. To 3. Here it comes. Bear with me. So stacked cells, this is what we mean. In this case, sand mounds. So if we needed a sand mound that was 100 feet long, we could put in two 50-foot long sand mounds like this. And so we've got 7.5 meters, which is the SPM horizontal setback to drains, and we've got 3 meters as an upslope separation from the second system. So that's what we mean by stacking cells. It implies that you've got a lot of land, I suppose, but it can fit into a narrower site as long as you've got the land to do this. So that's another thing that we can do as ropes if we can't meet LLR. Some other options. As with all critical standards from Volume 2, ropes must support departures with written advice from a professional. So we need a relationship with a professional who understands something about this stuff, and somebody who's willing to give us a written advice for that particular departure without taking the whole job. I put up should and crossed it out because, you know, if we needed a system 100 feet long and we were able to fit in a system 95 feet long, you know, we have some latitude in these things. You know, perhaps I shouldn't say this in my role as compliance officer, but if you had some other mitigating strategy, like you used time dosing when you otherwise didn't have to, or you made the thing bigger or something like that, you can consider departing from these things. It's a professional reliance model, but I wouldn't go, past 10% without a professional. So the short version is we need to follow linear loading, and if we can't, we need to either stack cells, do an extended tow, or have a professional. Now the professional, we are responsible to make sure he or she knows what they're doing, and if you're a professional, then take note as well. The professional could consider an in situ mounding study. So that means digging a trench, putting pipe in it, adding water to it at a known volume, and monitoring it with a vertical standpipe in the ground so that we can stick a tape measure down there and actually measure the height of the increase in the mounding effect. In other words, we can measure how high up the saturated level comes. We can either, it takes about a week, in some cases more, so you got to dig this, you got to come back every day, add water, measure, or you can consider having the owners do that. The owners can turn on the hose and they can measure it. It sounds like a very onerous prospect, but if you can save 10 truckloads of sand, and if you can actually fit the thing on the site that you couldn't before, then it's well worth it. A lot of people who do this stuff say that it's justified just by the amount of money they save on sand. At this point, it's a little bit out of scope of practice for ropes, but Michael Payne is proposing to do some workshops on how to do this in situ mounding study. And I've talked to a lot of ropes who do it for him, and they say it's pretty cool, pretty easy. So stay tuned for that. If the training was available from Michael, or Michael and I, then the registration board could consider changing policy to include a linear loading departure based on this in our practice guidelines. So stay tuned, I guess. The other thing a professional can do is mounding calculations. Fairly fancy math that an advanced rope could probably take that on too, and we're considering some training for that. In other words, rather than follow the prescriptive standards in the linear loading rate tables, you could actually do the math to determine an estimated mounding effect, something your professional can do for you. Now the professional then, if he's going to make the system shorter, here's some examples of mitigating strategies the professional could consider. It could be time dosing or microdosing where it otherwise wasn't required, because you're making it less wet, right? Which would decrease the mounding effect. The other way would be increasing AIS, make the thing bigger. Again, you're making every cubic meter of the soil less wet. Increased VS, same idea, I guess. You're having a higher elevation above the seasonal high water table, so therefore some mounding effect is not going to decrease the VS so much that you're not meeting the standard because you had extra in the first place. So those can be mitigating strategies a professional could consider, but what they can't consider is improved pretreatment. Type 2 or 3, it's not relevant to linear loading. SPM linear loading rate selection has nothing to do with effluent quality. There's no distinct columns for type 1, 2, or 3. There is for hydraulic loading, but not for linear loading. And the reason is because it's irrelevant, right? I mean, we still need a certain amount of VS, and it doesn't matter what type it is. You still need to have some degree of unsaturated soil. So that is, we've come to the end, gang. I feel like I've been talking to myself. You guys have been a silent bunch. But now some time for some questions and discussion. Hope somebody has something. I think what I'm going to do is I'm going to stop the recording. And I'll just stop showing my screen for just a minute. I'll stop the recording.